Ever get tricked by a really cool optical illusion? Like one of those pictures that messes with your eyes?
Yeah, I know what you mean.
Well, imagine that, but on like a cosmic scale.
Oh, wow.
Because the James Webb Space Telescope just captured something super cool.
What is it?
They're calling it a cosmic mirage. It's actually an Einstein ring.
Oh, an Einstein ring.
Yeah, have you seen this picture?
I have, yeah, and it's absolutely stunning.
It's incredible.
Yeah.
And you know what's really cool about this is
What?
it's not just a pretty picture.
Right.
We can actually use it to learn stuff.
Oh, yeah, totally.
You know, imagine a distant galaxy way, way out there.
Okay.
And its light is being bent and stretched into this ring shape.
That's cool.
Yeah, by the gravity of a galaxy that's closer to us.
I see. So we've got a distant galaxy and a closer galaxy.
Yeah.
And the gravity from that closer galaxy is affecting the light from the distant one. Got it. So it's like the universe is giving us this natural magnifying glass.
Oh, that's a good way to put it.
Right.
Yeah, that helps me visualize it.
So think about like if you have a bowling ball.
Okay.
And you put it on like a stretched out rubber sheet.
Right.
It creates like a dip, right?
Right. It sinks in.
Yeah. And then imagine light from that background galaxy sort of rolling past this dip. It's going to get curved.
I see, yeah.
Right.
That makes sense.
And when the alignment is just right, we see this incredible circular form.
Wow.
Isn't that wild?
That's amazing.
So this picture is definitely like picture of the month material.
Oh, yeah, for sure.
So our mission today is to like kind of unpack this whole cosmic illusion thing.
Yeah.
And see what we can learn from it.
I'm excited.
All thanks to Webb.
Yeah, Webb is giving us so much good stuff.
So the whole thing that makes this work is called gravitational lensing.
And this was actually predicted by Einstein.
Oh, wow.
Back in the day.
Yeah, way back when.
In his general theory of relativity.
Right. So like over 100 years ago, he figured this out.
Yeah. Isn't that incredible?
It's mind-blowing.
So basically, he said that massive objects like galaxies actually warp space-time.
Right.
And this warping, it bends the path of light. So the foreground galaxy, the one that's closer to us, is acting like a lens. It's focusing and distorting the light from that distant galaxy behind it.
So cool.
Right. So the foreground galaxy is bending the light from way behind it.
Right.
But to get that perfect ring shape, doesn't everything have to be in like a really specific arrangement?
Yeah, absolutely.
Yeah.
You need a very specific lineup for it to work.
Right.
Yeah, so for a complete Einstein ring to form the background galaxy, the lensing galaxy, and the Webb telescope all have to be almost perfectly aligned.
Oh, wow.
And the more precise the alignment, the more complete and well-defined that ring will look to us.
That is so crazy to think about.
It really is.
Like on a cosmic scale, everything has to be lined up so perfectly for us to see this.
Makes you realize how much we don't see.
Right.
Yeah, how many of these things are probably out there.
Just because things aren't lined up?
Right, exactly.
That's a good point.
Yeah.
So this particular ring in the picture, can you tell us a bit more about the galaxies that are involved in making this happen?
Yeah, so the galaxy that's acting as the lens, the one in the center of the picture, that's an elliptical galaxy.
Oh, okay.
Yeah, and you can really see its bright core, which is really concentrated.
Okay.
And then just the overall shape of the galaxy is super smooth.
Yeah.
Almost featureless.
I see.
Now this galaxy,
Yeah.
it's not just floating out there on its own.
Right.
It's actually part of a galaxy cluster.
Oh, okay. What's that?
So that's a huge group of galaxies, all bound together by gravity.
Wow.
Yeah, and this particular cluster is known as SMA CSJ 00028.27537.
Okay.
Yeah, a very catchy name.
Easy to remember.
Right.
Yeah.
So being part of this cluster, it definitely influences the lensing effect.
Oh, how so?
Well, the combined gravity of all those galaxies in the cluster really amplifies the warping of space-time.
I see.
Making the lensing effect even stronger.
That makes sense.
Yeah.
So what about the ring itself?
Right.
Like the warped light?
Yeah.
What galaxy is that coming from?
So that light originates from a spiral galaxy.
Okay.
Much, much farther away.
Wow.
Yeah. And what's really amazing is that even though the light is bent and stretched, Webb's resolution is so good that we can actually make out individual star clusters.
Oh, wow.
In that distant spiral galaxy.
That's incredible.
And even some of the gas structures within it.
Oh, wow.
It's mind-blowing.
That's so cool. So we can actually see the stuff that this galaxy is made of.
Right, and we can use that information to analyze its star formation rate in the early universe.
That's so cool.
Yeah, which is something that we couldn't do before.
Right.
For galaxies this far away.
Yeah, it's like opening up a whole new window into the past.
Exactly.
Isn't that incredible?
It really is.
So it's not just a beautiful picture.
No.
It's giving us all this data on how galaxies formed billions of years ago.
Billions of years ago.
So cool. And I understand this observation wasn't just like a lucky find. It was part of a bigger research project.
Right. It was part of a survey.
Oh, okay.
Yeah.
What was it called?
It's called the Strong Lensing and Cluster Evolution Survey.
Oh, wow.
Or SLICE.
A SLICE. Okay.
Yeah.
Cool.
And this project is led by Guillaume Mahler.
Okay.
And it aims to study how galaxy clusters, like the one we're talking about, have evolved over the past 8 billion years.
8 billion years.
Yeah. So they're looking at a huge chunk of time.
That's like almost half the age of the universe.
Right.
It's mind-blowing.
Yeah.
So they're observing a total of 182 different galaxy clusters.
Okay.
Using Webb's near-infrared camera, or NIRCam.
Right.
Which is really sensitive to the faint light from these really distant objects.
Right, which makes it perfect for this kind of research.
Yeah, so they're really trying to, like, maximize the data they can get.
Exactly.
So cool.
Yeah.
And it's not just Webb that's involved here, right?
That's right.
It's a team effort.
It is. Yeah. This image is enhanced by data from the Hubble Space Telescope as well.
Oh, cool.
Yeah.
So they're using both.
Yeah. They're using data from Hubble's Wide Field Camera 3 and the Advanced Camera for surveys.
So they're combining, like, the best of both worlds.
Right.
To get the best possible picture.
Exactly. And it gives us a much richer and more detailed view of this cosmic phenomenon.
What a great example of, like, scientific collaboration.
Absolutely.
I love that.
Yeah, it's really cool.
So to bring it all together, this amazing Einstein ring, revealed in such detail by Webb with help from Hubble, it's not just visually striking, it's a powerful tool for understanding the universe.
It's like a natural magnifying glass.
Yeah.
Created by gravity.
Right.
Allowing us to see deeper into the universe.
Yeah.
And study distant galaxies.
That we couldn't see otherwise.
Exactly.
It really makes you think about how these abstract concepts, like the curvature of space-time, can lead to such incredible observations.
Yeah.
Both visually and scientifically.
And it just shows you how interconnected everything is. Right. In the cosmos.
Yeah, and it makes you wonder, like, what else is out there?
Right.
What other cosmic mirages are waiting to be discovered?
That's a great question. And I think with Webb, they're just scratching the surface.
I can't wait to see what we find next.
Me too.
It's going to be an exciting future.
Absolutely.
This is going to be awesome.
Yes.
I love this stuff.
Me too.
It's so cool.
Really is mind-blowing.
All right. Well, thanks for joining us today.
Yeah, thanks for having me.
This has been another deep dive.
It has been great.
Into the mysteries of the universe.
Yeah.
Stay tuned for more.